subscribe button right under the video and also the bell icon to get notification on any of our latest updates on our videos.
Hello and welcome to another Smart Book Eyes tutorial. My name is Fatima and today we are going to explore applied mechanics in the aspect of force couple systems. So, a couple is the combined moment of two equal, opposite and non-collinear forces. And here are a couple of representations. As we can see from here, the magnitude of these two forces is the same, but they are pointing at opposite directions. That's why one is positive and the other is negative. And the distance between them, this separation distance, is denoted by d. Now this and this, it doesn't matter in which way the system is skewed, it's basically represented by such a diagram. That's from here going here, this is the distance, and another arrow coming here. And the forces are also non-collinear because their lines of actions are parallel and they will never intersect. Now the moment of a force couple system is basically given by force times distance, and it can be either counterclockwise or clockwise. Now the way I normally determine whether a force will be acting in a clockwise direction or in an anti-clockwise direction or counterclockwise direction is by assuming that the point of action of the force is like a circle, something like this, and I'll ask myself, if a force is acting in this direction and another is pushing it in this direction, in which way will the circle turn? Will it be in a clockwise direction, like the motion of a clock arm, or will it be in the opposite direction, which is the counterclockwise direction? Now, as we can see, if we were to put this circle here, and we let this force act on it, or perhaps it might be in the center, and this force is pushing it in this direction while the other one is pushing it in this direction, then definitely it will turn in the right, that's the clockwise direction. On the other hand, if we were to put the circle here, and this is pushing it in this direction while this other one is pushing it in this direction, it will turn in the opposite direction, which is the counterclockwise direction. So now it will depend on your sign convention, whether you're using a positive counterclockwise and a negative clockwise, or vice versa. That will depend on your choosing sign convention. So let's take an example. This is the example. We're asked to calculate the moment of the 1200 Newton force about pin A of the bracket, and we should begin by replacing the 1200 Newton force by a force couple system at point C. Now we can see that this force is not straight, it's going in this direction, and we're given a small triangle to indicate the angle to the horizontal or the vertical. It depends on which one we decide to use. So if we decide to use this small angle here, we can say tan theta is equal to 1/2, and our theta will now be equal to tan inverse of 1/2, which is going to be equal to 26.57 degrees. Now we're asked to first replace this force by a force couple system at point C, and to get the force couple system we'll have to multiply the force with the separation distance between C and the line of action of the force. Now we can see this is a circle and it has a radius of 200 millimeter, which is equal to 0.2 meters. So our separation distance D is 0.2, and this is our force. So we'll have our M is equal to FD, which is equal to 1200 newtons times 0.2 meters, which is equal to 240 Newton meters. Now, in which direction? We can confirm the direction by saying, so if this force acts in this direction, then how will this circle move? Obviously it will go this way, which is counterclockwise. That's counterclockwise. Right, so or if we like, we can put a small arrow here to denote the counterclockwise movement. Then, so this is like a mini representation of the question. The first was here before, and now when we are replacing the first with the first couple system at C, it will be something like this, with the same angle here and a moment. Going in this direction. Now, to find the overall moment, we'll also have to find the moment due to the force at this position and on this point. So ideally, to find the moment, we can either say our moment is equal to the force times the perpendicular distance, or we can resolve our m into x and y components. That's fx multiplied by the distance between the resolved x components and our point of application, then added to fy dy, that's the distance between our resolved y component and the point of application. So for this we can use both and compare our answers. Now if we are to use the first formula for this, where we'll have to get the perpendicular distance between C and A, we can think of transferring this force through here to this direction. It's still the same line of action, and then find a point where find the shortest distance between A and this line of action. That's the perpendicular distance. So we'll be left with the right angle triangle, something like this, and this is a right angle 90 degrees. So if we have this, from the question we're given the distance between point C and point A, which in this triangle looks like a hypotenuse. So we can check it out. That's 600 millimeters. So our hypotenuse here is 0.6 meters. 0.6 meters. And to find this perpendicular distance, we can simply use, our angle theta was also transferred to this point from its original position, and based on our theory of equal angles, this angle is the same as this angle, so we have angle C here to be our theta, which is 26.57 degrees. Therefore, we can use our value of the hypotenuse and our theta to find our perpendicular distance. To do that, we can say sine theta is equal to opposite over hypotenuse, right? We can say sine 26.57 is equal to D perpendicular over 0.6. This implies that our D perpendicular is equal to the cross multiplication of sine 26.57 and 0.6, right? 0.6 multiplied by sine 26.57, which is equal to 0.2684 meters. Now our moment will simply be our force, which is 1200 newtons, multiplied by this distance. So our moment from C to A is equal to 1200 newtons multiplied by 0.2684 meters. Which is equal to to 322.08 Newton meters. Now remember that we already have another moment here, so our total moment will be equal to the first moment we got, that's 240 Newton meters, added to this one. Now we can see that the second force is also acting in a counterclockwise direction, so there won't be any change in the sign we use. We are not going to change the sign for the second one too, so it's also counterclockwise. If it were clockwise, then one of them has to be negative because they are not going in the same direction. So our total M will now be equal to 240 plus 322.08 Newton meters, which is equal to 562.08 Newton meters in a counterclockwise direction. So that's it for this example. If you want to cross-check, you can cross-check using this formula. And the interesting thing is that if you were to resolve this first to give you x and y components, the x component, since both C and A are on the same line, the x component will also be on this axis, and there won't be any distance between the x component and the point A. So our fx dx will give you 0, our dx is 0, while for our fy dy, our fy will be in the y direction, that's a straight line, and its distance will simply be this distance, 0.6. Plus our fy is simply our value of f sine our angle theta, which is actually what is contained here. And when you multiply it by 0.6, it will actually give you the same value as the perpendicular distance, d perpendicular. So you can cross check it if you like, because this will give you 0 and this will give you the same value as 322.08 Newton meters in the counterclockwise direction, and you can add it to the original, the initial moment you have by converting it to a first couple system. So that's it. Thanks for watching.